Hello, welcome back. Today I will dedicate my time again to the GCP Elastic Cloud infrastructure. It's about scaling and automation. This is the second episode, so I will basically go through the whole course for like 4 or 5 videos. The course is this one. It says 7 hours here. So let's have a look where we are. Okay. Last time I completed the interconnecting networks module, and yeah, it was an easy one. The lab was quite boring. It was just command line commands to create um, yeah, VPN gateways, routers, to change firewall rules. It was just standard procedures to interconnect some VPCs. We simulated to have VPCs on premises and in cloud, which needed to be connected to shared services. And now we'll go for load balancing and auto scaling. So we put here the speed to 1.5, but let's have a look at the leaderboard here. Let's see what's the situation. We still have to resist for 2 days to pass to the Diamond League. Okay, and we're sixth, so we're still in top 10, but everybody's getting closer. So we have just one day of advantage here. I will say to push and to arrive at least at 3,000. So we get in the top five. Otherwise, yeah, even these people will be able to arrive to us and surpass. That would not be good. Will be the second week we cannot arrive to the Diamond League. So let's go. Load balancing and auto scaling.
Focus on load balancing and auto scaling. Cloud load balancing gives you the ability to distribute load balanced compute resources in single or multiple regions to meet your high availability requirements, to put your resources behind a single Anycast IP address, and to scale your resources up or down with intelligent auto scaling. In this
So I
module, we
will
focus on load
need to
balancing and auto
replay it.
scaling. Cloud load balancing gives you the ability to distribute load balanced compute resources in single or multiple regions to meet your high availability
It's
requirements.
kind of fast.
Cloud
I'm
load
not
balancing
following.
gives you the ability to distribute load balanced compute resources in single or multiple regions to meet your high availability requirements, to put your resources behind a single Anycast IP address, and to scale your resources up or down with intelligent auto scaling. Using cloud load balancing, you can serve content as close as possible to your users on a system that can respond to over 1 million queries per second. Cloud load balancing is a fully distributed, software defined, managed service. It is not instance or device based, so you do not need to manage a physical load balancing infrastructure.
Google Cloud offers different types of load balancers that can be divided into two categories, global and regional. The global load balancers are the HTTPS, SSL proxy, and TCP proxy load balancers. These load balancers leverage the Google frontends, which are software defined, distributed systems that sit in Google's point of presence and are distributed globally. Therefore, you want to use a global load balancer when your users and instances are distributed globally, your users need access to the same applications and content, and you want to provide access using a single Anycast IP address. The regional load balancers are external and internal HTTPS and TCP proxy. These are also internal TCP UDP and external TCP UDP network load balancers. The internal and network load balancers distribute traffic to instances that are in a single Google Cloud region. The internal load balancers use external TCP UDP network load balancers. The internal and network load balancers distribute traffic to instances that are in a single Google Cloud region. The internal load balancers use Andromeda, which is Google Cloud's software defined network virtualization stack, and the network load balancer uses maglev, which is a large distributed software system. The internal load balancer for HTTPS traffic is a proxy based regional layer 7 load balancer that enables you to run and scale your services behind a private load balancing IP address that is accessible only in the load balancers region in your VPC network.
In this
Okay.
module, we will cover the different
So
types of
we
load balancers that are
had
available in
an
GCP.
overview
We
about
will also
the
go over the
type of
and their
load
autoscaling
balancers.
configurations, which can be used by these load balancing configurations. You will explore many of the covered features and services throughout the 2 labs of this module, and I will wrap things up by helping you determine.
But yeah, I will mark it as completed.
A managed instance group is a collection.
Let's see if there's any documentation about load balancers. And well, I have also another idea. I have some documentation here, external guide study cases, no, miscellaneous. So maybe have here in these schemes something that can visually explain me the differences between the type of balancers. Okay, application development deployment now. VPC shadowing, VPC peering, VPN. This is the thing that we did last time. And here we shouldn't have, okay. So we have the CDN, which is a Google Global Edge Network to serve content closer to users. Okay. So CDN looks like something related to as to load balancers. So I remember the cloud NATs. Yeah, this is something we created and allows virtual machines without external IP address to connect to the internet. This instead looks like configuration for being reachable from external IPs. Okay, so HTTPS load balancers. What it is, a load balancer for HTTP traffic. Okay, SSL proxy, it's a load balancer for TCP with SSL offload. TCP proxy is a load balancer for TCP without SSL. Network load balancer, it's a load balancer for TCP UDP without SSL. Internal load balancer is a load balancer for TCP UDP regional. Okay, so all difference here looks like it's not the protocol. So we're always working at HTTP or TCP level. But it changes how we are contacting these load balancers. So in HTTPS load balancers, we are contacting from the external networks globally. For the SSL, we are contacting also from global external sources. TCP proxy is the same. Network load balancer are contacted from regional peers in any port. Internal load balancers are also regional or internal, as it says. And Kubernetes load balancing is a particular case that allows you to balance between your application running in Kubernetes. Okay. Okay. Kind of strange. So public address, dedicated shard. This is VPN, but I just had the VPN lab. Okay, so it's kind of confused, I would say. It doesn't really clarify to me. I mean, it's kind of obvious what's writing here. The names are already saying it. I wouldn't say this is a really good schema by this guy Amit. I mean, there are some other pages which are great, but this may make sense for him. But for me, it's like it's not giving me something like a principle to understand and discern which is the best load balancer for the different use cases. So yeah, great, but let's see his personal website. Oh, wow, this is a nice website. I'm a daydreamer and April. You may know me as CC with dreams, or the the guy who created startcloudnow.com, or the guy who makes awesome GCP exam prep sheets, and there will tell stories about his career and so on LinkedIn. Well, I'm the same guy, and I'm developer relations engineer. Cloud network at Google. So what I'm working on? What the fuck does mean? Developer relations engineer. Wow. Yeah. Interesting. He has a Medium. Yeah, nice. And also Discord. The Twitter. I would never call it X. So yeah. We'll see. Not that useful in the end. But yeah, let's continue. Maybe we'll understand in a better way. Oh, let's see if in Google's documentation, GCP load balancer, cloud load balancing, high performance scalable load balancing on Google Cloud, scalable load balancing on Google Cloud with high performance. Choose the best load balancer type for you with this guide. Oh, nice. Choose a load balancer. This document helps you determine which Google Cloud Balancer best meets your needs. To see an overview of all the cloud load balancing products available, see Google Cloud Load Balancing Overview. To determine which cloud load balancing product to use, you must first determine what traffic type your load balancer must handle. As a general rule, you choose an application load balancer when you need a flexible feature set for your applications with HTTPS traffic. You choose a proxy network load balancer to implement TCP proxy load balancing to backends in one or more regions. And you choose a pass-through network load balancer to preserve client source IP addresses, avoid the overhead of proxies, and to support additional protocols like UDP, ESP, and ICMP. You can further narrow down your choices depending on your application's requirements, whether your application is external, internet-facing, or internal, and whether you need backends deployed globally or regionally. The following diagram summarizes all the available deployment modes for cloud load balancing. So applications, load balancer, HTTP, HTTPS. So we receive maybe a REST API requests from the external internet. Globally, we'll use a global external application load balancer. Have a regional external load balancer, and then we have internal options also. But yeah, it's kind of obvious. I mean, it's just remembering these layers of decision. I'm not sure. Network load balancer. It will be a proxy or a pass-through. The proxy will hide the IP, for what I understand, as this is the main thing they pronounce when using a pass-through, which will allow the information about the source of the request to be identified. Okay. We'll ask this guy here to explain us differences between GCP load balancers. First, explain application HTTPS vs network. So let's see the key differences between load balancer vs application load balancer vs network load balancer. So it looks like, first of all, we are working on different protocol, and this was clear. Layer 7 application layer, so all the logics in the body will be applied at that level. Instead, in layer 4, we'll have TCP packets. We'll use the TCP protocols, protocol routines. So use cases for HTTP, it's routing web traffic, managing web apps, content-based routing. Instead here, handling high performance, low latency raw network traffic. So we are managing the packets. Instead here, advanced features, SSL termination, URL path-based routing, global load balancing, simple load distribution, regional load balancing. Then here we have backends like GCE instances, JKE, Cloud Run, and App Engine. Instead here, GCE instances, regional backend services. Web applications with complex routing needs, low latency, high throughput scenarios, gaming, web, etc. Why these differences? I mean, I want to go deeper. Like application load balancers operates at layer 7, which understands application level protocols like HTTP, HTTPS. It processes requests at content level, enabling feature like URL path routing and SSL termination. Instead, the network load balancer focuses on raw packet distribution. It doesn't inspect application content, making it faster and better for low latency needs. Okay. Processing overhead. Therefore, an application load balancer requires more processing power to analyze and route based on application data. This enables smarter routing but can introduce slightly more latency. Instead, the network load balancer simply distributes packets based on IP and port, minimizing latency and maximizing performance for traffic. Use case optimization. So for example, application load balancer is designed for web apps needing smart routing, centralized SSL management, or global load balancing. Instead, network load balancer built for workloads requiring fast, simple, and efficient traffic routing, like real-time gaming, IoT, and financial trading. Global vs regional. So global for HTTPS. Web applications often span multiple regions, so global traffic management is critical. Many raw network protocols and regions are specific for performance or legal reasons. Okay, therefore, with an application load balancer, when the data arrives to the machine, to the target machine, it will already be sure that it will be in the context will be auto-determined. Therefore, the machine will need to just activate. The machine will implicitly have the context as the data arrive to it. Instead, the network load balancer will not have information at application level when data arrives, plus who sends. The communications are not based on functions. Instead, the packets are distributed only on region. The target machine will need to extract the context from the packets. Please comment our machine receive request from external establish the terminal balancer. No application awareness. Okay. Explicit content extraction. Focus on web application and smart and easy request handling, prioritize open fixing network level loads. Can you make up a use case in which both solution will be usable and make a list of pros and cons with numbers? Multiplayer online game service. Imagine a company hosting a popular multiplayer online game. The game has two main components: web interface for account management, purchasing game items, and leaderboards. Game servers handling real-time gameplay traffic for low latency multiplayer interaction. Both an application load balancer and a network load balancer can be used as they serve different parts of the architecture. So the application load balancer manages the web interface traffic routing requests to backend web servers. Instead, the network load balancer distributes game session traffic to appropriate game server. So performance processes 10,000 HTTP requests, handles millions of packets a second with minimal latency. Complex routing can route based on path host names and query parameters. Routing limited to IPs and ports, no content-based decision. Session management provides sticky sessions or cookie-based routing for user data. Scalability auto-scales globally. Protocol support. Ease of debugging. Okay. Setup complexity. Easier provides built-in features, more manual setup for advanced use like custom session persistence. Higher cost due to processing overhead, lower cost, and it's optimized for packet distribution. Account portals, leaderboards, or APIs session for real-time gameplay and low latency traffic. Why use both? Okay, now I maybe have an idea. Yeah, maybe then I will have to understand it better, but for now, I have this fundamental division, which is the
A managed
global
instance group is a
application
collection of
versus
identical VM
network.
instances that you control as a single entity using an instance template. You can easily update all the instances in a group by specifying a new template in a rolling update. Also, when your applications require additional compute resources, managed instance groups can scale automatically to the number of instances in the group. Managed instance groups can work with load balancing services to distribute network traffic to all of the instances in the group. If an instance in the group stops, crashes, or is deleted by an action other than the instance group's commands, the managed instance group automatically recreates the instance so it can resume its processing tasks. The recreated instance uses the same name and the same instance template as the previous instance. Managed instance groups can automatically identify and recreate unhealthy instances in a group to ensure that all instances are running optimally. Regional managed instance groups are generally recommended over zonal managed instance groups because they allow you to spread the application load across multiple zones instead of confining your application to a single zone or having you manage multiple. Regional managed instance groups are generally recommended over zonal managed instance groups because they allow you to spread the application load across multiple zones instead of confining your application to a single zone or having you manage multiple instance groups across different zones. This replication protects against zonal failures and unforeseen scenarios where an entire group of instances in a single zone malfunctions. If that happens, your application can continue serving traffic from instances running in another zone in the same region. In order to create a managed instance group, you first need to create an instance template. Next, you're going to create a managed instance group of n specified instances. The instance group manager then automatically populates the instance group based on the instance template. You can easily create instance templates using the Cloud Console. The instance template dialog looks and works exactly like creating an instance, except that the choices are recorded so they can be repeated. When you create an instance group, you define the specific rules for that instance group. First, you decide what type of managed instance group you want to create. You can use managed instance groups for stateless serving or batch workloads, such as website frontend or image processing from a queue, or for stateful applications, such as databases or legacy applications. Second, provide a name for the instance group. Third, decide whether the instance group is going to be single or multi-zoned, and where those locations will be. You can optionally provide port name mapping details. Fourth, select the instance template that you want to use. Fifth, decide whether you want to autoscale and under what circumstances.
Okay, let's go.
Finally, consider creating a health check to determine which instances are.
Let me provide more details on the autoscaling and health checks of a managed instance group. As I mentioned earlier, managed instance groups offer autoscaling capabilities that allow you to automatically add or remove instances from a managed instance group based on increases or decreases in load. Autoscaling helps your applications gracefully handle increases in traffic and reduces cost when the need for resources is lower. You just define the autoscaling policy, and the autoscaler performs automatic scaling based on the measured load. Applicable autoscaling policies include scaling based on CPU utilization, load balancing capacity, or monitoring metrics, or by a crew-based workload like pub sub or schedule such as start time, duration, and recurrence. For example, let's assume you have two instances that are at 100% and 85% CPU utilization as shown on this slide. If your target CPU utilization is 75%, the autoscaler will add another instance to spray out the CPU load and stay below the 75% target CPU utilization. Similarly, if the overall load is much lower than the target, the autoscaler will remove instances as long as that keeps the overall utilization below the target. Now, you might ask yourself, how do I monitor the utilization of my instance group? When you click on an instance group or even an individual VM, you can choose to view different metrics. By default, you'll see the CPU utilization over the past hour, but you can change the time frame and visualize other metrics like disk and network usage. These graphs are very useful for monitoring your instance's utilization and for determining how best to configure your autoscaling policy to meet changing demand. If you monitor the utilization of your VM instances in cloud monitoring, you can even set up alerts through several notification channels. A link to more information on autoscaling can be found in the course resources for this module.
Okay.
Another important configuration for a managed instance group and load balancer is a health check. A health check is very similar to an uptime check in cloud monitoring. You just define a protocol, port, and health criteria, as shown in the screenshot. Based on this configuration, Google Cloud computes a health state for each instance.
Now let's talk about HTTPS load balancing, which acts at layer 7 of the OSI model. This is the application layer, which deals with the actual content of each message, allowing for routing decisions based on the URL. GCP's HTTPS load balancing provides global load balancing for HTTPS requests destined for your instances. This means that your applications are available to your customers at a single Anycast IP address, which simplifies your DNS setup. HTTPS load balancing balances HTTP and HTTPS traffic across multiple backend instances and across multiple regions. HTTP requests are load balanced on port 80 or 8080, and HTTPS requests are load balanced on port 443. This load balancer supports both IPv4 and IPv6 clients, is scalable, requires no pre-warming, and enables content-based and cross-regional load balancing. You can configure URL maps that route some URLs to one set of instances and route other URLs to other instances. Requests are generally routed to the instance group that is closest to the user. If the closest instance group does not have sufficient capacity, the request is sent to the next closest instance group that does have the capacity. You will get to explore most of these benefits in the first lab of the module. Let me walk through the complete architecture of an HTTPS load balancer by using this diagram. A global forwarding rule directs incoming requests from the internet to a target HTTP proxy. The target HTTP proxy checks each request against a URL map to determine the appropriate backend service for the request. For example, you can send requests for www.example.com/audio to one backend service, which contains instances configured to deliver audio files, and the requests for www.example.com/video to another backend service, which contains instances configured to deliver video files. The backend service directs each request to an appropriate backend based on serving capacity, zone, and instance health of its attached backends. The backend services contain a health check, session affinity, a timeout setting, and one or more backends. A health check polls instances attached to the backend service at configured intervals. Instances that pass the health check are allowed to receive new requests. Unhealthy instances are not sent requests until they are healthy again. Normally, HTTPS load balancing uses a round-robin algorithm to distribute requests among available instances. This can be overridden with session affinity. Session affinity attempts to send all requests from the same client to the same virtual machine instance. Backend services also have a timeout setting, which is set to 30 seconds by default. This is the amount of time the backend service will wait on the backend before considering the request a failure. This is a fixed timeout, not an idle timeout. If you require longer-lived connections, set this value appropriately. The backends themselves contain an instance group, a balancing mode, and a capacity scaler. An instance group contains virtual machine instances. The instance group may be a managed instance group with or without autoscaling, or an unmanaged instance group. A balancing mode tells the load balancing system how to determine when the backend is at full usage. If all the backends for the backend service in a region are at the full usage, new requests are automatically routed to the nearest region that can still handle requests. The balancing mode can be based on CPU utilization or requests per second. A capacity setting is an additional control that interacts with the balancing mode setting. For example, if you normally want your instances to operate at a maximum of 80% CPU utilization, you would set your balancing mode to 80% CPU. Let me walk through.
So just a question, my friend here. Why GCP backends send requests to mix? No, the question will be, do GCP backends send requests only to mix, or is it possible to send a backend service request to a JK cluster, for example? I'm not sure if it's a stupid question. Oh, okay, here's an overview. Okay, so you can send them to Mix, JK, serverless backends. Great, okay. Okay, so it's just the example here.
Through an HTTP load balancer in action. The project on this slide has a single global IP address, but users enter the Google Cloud Network from two different locations, one in North America and one in EMEA. First, the global forwarding rule directs incoming requests to the target HTTP proxy. The proxy checks the URL map to determine the appropriate backend service for the request. In this case, we are serving a guestbook application with only one backend service. The backend service has two backends, one in US Central 1A and one in Europe West 1D. Each of those backends consists of a managed instance group. Now, when a user request comes in, the load balancing service determines the approximate origin of the request from the source IP address. The load balancing service also knows the locations of the instances owned by the backend service, their overall capacity, and their overall current usage. Therefore, if the instances closest to the user have available capacity, the request is forwarded to that closest set of instances. In our example, traffic from the user in North America would be forwarded to the managed instance group in US Central 1A, and the traffic from the user in EMEA would be forwarded to the managed instance group in Europe West 1D. If there are several users in each region, the incoming requests to the given region are distributed evenly across all available backend services and instances in that region. If there are no healthy instances with available capacity in a given region, the load balancer instead sends the request to the next closest region with available capacity. Therefore, traffic from the EMEA user could be forwarded to the US Central 1A backend if the Europe West 1D backend does not have capacity or has no healthy instances as determined by the health checker. This is referred to as cross-region load balancing. Another example of an HTTPS load balancer is a content-based load balancer. In this case, there are two separate backend services that handle either web or video traffic. The traffic is split by the load balancer based on the URL header as specified in the URL map. If the user is navigating to /video, the traffic is sent to the backend video service. And if the user is navigating anywhere else, the traffic is sent to the web service backend. All of that is achieved with a single global IP address.
Great.
A HTTPS load balancer has the same basic structure as a HTTP load balancer, but it differs in the following ways. A HTTPS load balancer uses a target HTTPS proxy instead of a target HTTP proxy. A HTTPS load balancer requires at least one signed SSL certificate installed on the target HTTPS proxy for the load balancer. The client SSL sessions terminate at the load balancer. HTTPS load balancers support the Quick Transport Layer Protocol. Quick is a transport layer protocol that allows for faster client connection initiation, eliminates head-of-line blocking in multiplex streams, and supports connection migration when a client's IP address changes. For more information on the Quick protocol, see the link in the course resources. To use HTTPS, you must create at least one SSL certificate that can be used by the target proxy for the load balancer. You can configure the target proxy with up to 15 SSL certificates. For each SSL certificate, you first create an SSL certificate resource, which contains the SSL certificate information. SSL certificate resources are used only with the load balancing proxies, such as a target HTTPS proxy or target SSL proxy, which we'll discuss later in this module. Backend buckets allow you to use Google Cloud Storage buckets with HTTPS load balancing. An external HTTPS load balancer uses a URL map to direct traffic from specified URLs to either a backend service or a backend bucket. One common use case is send requests for dynamic content, such as data, to a backend service, and send requests for static content, such as images, to a backend bucket. In this diagram, the load balancer sends traffic with a path of /love2fetch to a cloud storage bucket in the Europe North region. All the other requests go to a cloud storage bucket in the US East region. After you configure a load balancer with the backend buckets, requests to URL paths that begin with /love2fetch are sent to the Europe North cloud storage bucket, and all other requests are sent to the US East cloud storage bucket. A network endpoint group, or NEG, is a configuration object that specifies a group of backend endpoints or services. A
Network endpoint group is a configuration object that specifies a group of backend endpoints or services.
A common use case for this configuration is deploying services in containers. You can also distribute traffic in a granular fashion to applications running on your backend instances. You can use NEGs as backends for some load balancers and with Traffic Director. Zonal and Internet NEGs define how endpoints should be reached, whether they are reachable, and where they are located. Unlike these NEG types, serverless NEGs don't contain endpoints. A zonal NEG contains one or more endpoints that can be compute engine VMs or services running on the VMs. Each endpoint is specified by either an IP address or an IP:/port combination. An Internet NEG contains a single endpoint that is hosted outside of Google Cloud. This endpoint is specified by hostname fqdn:/port or IP port. A hybrid connectivity NEG points to Traffic Director services running outside of Google Cloud. A serverless NEG points to Cloud Run, App Engine, Cloud Function Services.
Let's apply what we just covered. In this lab, you configure an HTTP load balancer with autoscaling. Specifically, you create two managed instance groups that serve as backends in US Central 1 and Europe West 1. Then you create and stress test a load balancer to demonstrate global load balancing and autoscaling.
Great, let's go. So now we do this lab. Okay. And we will finish the video there. It says 2 hours, a lot of tasks, but I would like to finish it in half an hour. Let's see. We'll see what we can do. So, oh shit. Dashboard, okay. So now you see it, okay. Application, blah, 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 objectives, configure health check firewall role. So health checks determine which instances of application load balancer can receive new connections. The health checks probes to your load balanced instances come from addresses in the range. Oh, sorry. So they say which are healthy to receive connections. Okay, so health checks works on these IP ranges. Create the health check rule. So VPC network firewall. Notice existing ICMP, internal IP, and SSH firewall rules. Each Google Cloud project starts with default network and these firewall rules. Create firewall rule, and we will name it forward allow health checks. Network firewall. Create firewall rule, we'll name it like this. Network default. Specify targets, tags, allow health checks. So the target with this rule will be able to work on IPv4 on these IP ranges. And this other IP range. Specified protocols and ports. Protocols and ports. Make sure to include 22 in source IP ranges. Okay, select TCP and 48, port 80. Okay, click create. So we created the role. Great. Now create a NAT configuration using Cloud Router. So mechanism that use configure with external IP addresses. We'll set up a Cloud NAT service to allow these VM instances to send outbound traffic only through Cloud NAT and receive inbound traffic through the load balancer. Create a Cloud Root instance. So network service Cloud NAT, get started. What was that? Network services, network management tools, network services, network management tools, Cloud NAT, get started, gateway name, NAT config, default, US Central 1, region, what the fuck? Region is denied by resource location, what the hell, US Central 1, okay. Click Cloud Router and select Create New Router. NAT router US 1 without the point at the end. Click Create. Click Create. Wait until the NAT gateway starts to change to running before moving to the next task. Okay, so here maybe it will take a few minutes. No, it's already running. So task 3, create a custom image for a web server. So VM instances, create instance. Okay, let's go. Name web server. Okay. Oh shit. US Central 1, US Central 1A. Boot disk, change, show advanced configuration. What the fuck? Wait, what's happening here? Why it's not showing me all the stuff? Man, what the fuck? New action virtual machine. Wait. Compute engine VM instance. Wait an instance. Oh, I see. Now they changed the user interface. Wow, now you have this interface. Okay. So show advanced configuration. And duration rule, select keep putting this. But now I do not understand. Okay. So it's a keep boot disk in which section? Duration rule. Duration keep boots disk. Okay. Click select advanced option. What? Select what? Okay, select. So advanced option, networking. Networking is here. Network tags. Allow health checks. Okay. Network interfaces. Default. And for external IPv4, select known. External known. Done. Oh, jeez. External done. Oh, why? Man. Oh, I don't want a new network interface. I just want this to not have an external IPv4. Done. Okay. And create, right? Okay, create. So we have a news in the compute engine interface, compute engine instances creation interface. But yeah, just a minor modification. Now we have to SSH into the web server and install Apache. Okay. It'll take a few more seconds. Then we need to start the Apache server. Okay. SSH. Yeah, SSH. Oh shit. Okay. Now authorize. Okay. Okay. So we were saying this. Sudo apt-get update. So we update machine and then install Apache. Okay, when it's done, we start the service. And then to test the default page for the Apache server, run the following command. For localhost. Okay. The default page for Apache shows displayed. Okay, so set the Apache service to start at boot. In the web server SSH terminal, update RCD Apache enable. Select in Cloud Console, select web server, more action, reset. So action, reset. Reset will stop and reboot the machine. It keeps the same IP and the same persistent boot disk, but the memory is wiped. Therefore, if Apache service is available after reset, the update RC command was successful. Check the server by connection with SSH and then Apache status. Let's see. So the machine is right. Authorize. Okay. Now let's see the Apache status active and running. Therefore, if you see connection required and failed, no. The result should be okay. Verify that the boot disk will not be deleted when the instance is deleted. So on the VM instance page, click web server. Okay, go into details, boot disk. When deleting instance, skip disk. Okay. So imagine now we will delete it. Where was it? Storage. When deleting instance, keep disk. Okay. Return to the Vim instance page, more actions, delete. Okay. So we delete the web server. Okay. In disks, verify web servers disk exists. Okay, so let's see. It's still deleting the web server. Create custom image. So in the left pane, click images, create image, my web server, disk web server, click create. So when it's done, it takes a while, okay. So we close this as we're deleting the machine. Instance deleted. And here we'll do refresh. We still have this disk. Therefore, we go to images, create new image. Image name, my web server disk, source disk, web server, create. Note, you have created a custom image that multiple identity web servers can be started from. At this point, you could delete the web server disk. Wow. Create a custom image for a web server. So images. Still creating it. Check my progress to verify the objective. Let's see if it's already taking it. Oh, it's saying yes, we can go forward. So configure an instance template and create an instance group. Create instance groups. So go to Compute Engine Instance Templates. Then my web server template, location global, ep02 micro, shard core. Global shard core ep02 micro. Boot disk change. Where is the boot disk? Here. And we'll use custom images for source projects for images. Make sure that Quick Labs project is selected. Yeah. Custom images. Okay. Image, my web server. select advanced options. Okay. And here we configure network tags, allow health checks, default, and no external IP. So for default, we put known as external IP, done. Then create. Okay, create the health check for managed instance group. So compute engine health checks, create health check, HTTP health check. Okay, so the health check is somewhere here. Okay, TCP 80. Okay, click create. Managed instance group health checks proactively signal to delete and create instances that become unhealthy. So create managed instance group. Managed instance group in US Central 1 and one in Asia East 1 instance group. Create instance group US 1 managed instance group. Okay. This will be the name. Managed template. Multiple zone US. Okay. For auto scaling, enter minimum number of instances 1 and maximum 2. Auto scaling signals, click CPU utilization. For signal type, select HTTP load balancing utilization. Enter target HTTP load balancing utilization to 80. Click done. Click initialization period at 60 seconds, okay? Manage instance group offer auto-scaling capabilities that allow you to automatically add or remove instances from a managed instance group based on increases or decreases in load. Auto-scaling helps your application gracefully handle increases in traffic and reduces costs when the need for resources is lower. You just define the auto-scaling policy and the autoscaler performs automatic scaling based on measured load. Auto healing for our health check type, health, HTTP health check. The initial delay, type 60. This is how long the instance group waits after initializing the boot up of a VM before it tries a health check. You don't want to wait 5 minutes for doing this, so you set it to 1 minute. And we put it to 30 seconds. Create and confirm. Wait a few minutes for the instance group to be created before repeating the same procedure for Notus 1 MIG. Click refresh until status change transforming. Okay. So now creating status. So we are waiting for the group managed group to be created. It's going through all the auto hearing policies, auto scaler policies. Okay, it was created. Now create another instance group, which we'll call like this, not US1 MIG. So this one, multiple zones, Asia is 1, auto scaling. HTTP load balancing utilization. This will be at 80 and then initialization period 60. Okay, and then for health check, select HTTP health check. Create and confirm. It's still waiting for the other. Oh no, it's completed, okay. But yeah. Verify the backends. So verify that VM instances are being created in both regions. VM instances, notice the instances start with USMIG. The instances are part of the managed instance group. So if we go to VM instances, we'll find out. Okay. Task 5, configure the application load balancer. Configure the application load balancer to balance traffic between the two backends as illustrated in the network diagram. Okay. So we'll have a request from internet. Global forwarding rule will choose the target proxy. Then a URL map will choose the right backend service, and then we'll have one of these being chosen. Okay, start the configuration. So let's go to network services load balancing. Create a load balancer imagine. Type of load balancer set application load balancer, public facing or internal public facing. So application public facing, best for global workloads. Global external application load balancer. Okay, let's see if I remember everything. Application, next. Public facing, next. Best for global workloads, next. And then global application load balancer, next. Create load balancer configure. Load balancer name. So configure the front end. Click front end configuration. Protocol HTTP4, IPv4, IP address ephemeral port 80. done. And then add front-end IP and port. Okay, IPv6 auto allocate port 80. Click done. So application load balancing supports both IP versions, client behavior determined by global and proceed over IPv4 to your backends. Okay. Configure the backend. Click backend configuration, backend service, create backend service, HTTP backend. HTTP backend, instance group, US MIG1. Port numbers, 80, balancing mode rate. Maximum RPS, request per second, 50. Capacity, 100. Oh, no! What? No, che porcata. Click add backend. Instance group, not US, port numbers, 80, rate. Maximum backend utilization, balancing mode utilization. 80, capacity 100. Okay, done. For health check, select HTTP health check. Click checkbox for enable login checkbox. Sample rate 1, click create. Okay. Click OK. Review and create HTTP load balancer. Click review and finalize. What? Review the backend services and front end. Now that the IPv4 and load balancer instead they will be referred as okay, not the IPv4 and 6 addresses to the load balancer. What? Wait. I could create. And now we take note. Okay, so we nearly concluded this. We are close to the end of this lab. taking its time. Well, it's a global service. It's deploying a lot of resources, maybe, or complex configurations. Yeah, let's see. Okay, now we have it. So this is our, wait. Okay, so this is the IPv4. This is the IPv6. Okay. Check my progress. Now we have it. So stress test the application load balancer. The application load balancer should forward traffic to the region that is closest to you. Access the application load balancer. So activate Cloud Shell continue. Yeah. And now to check the status of the load balancer, run the following command: replace LB IPv4 with the IPv. Okay. So instead of IPv4, we should put the IPv4. And the IP is this one. Open a new tab in your browser and navigate to make sure the load balancer with the preloader swift. Okay. So HTTP let's go. Since this site can't be reached, but wait, okay. Create a new machine, with the loads, then determine which service. Okay, so create instance stress test. Stress test, US Central 1. Okay, closer to the zone from the region, ep02 micro. So US Central 1. What? Wait. A region different but closer to US Central 1. And how can I choose another one if they're just allowing me this? Ah, fuck. I cannot select another one. There's something strange. Because there is closer, traffic should be forwarded to US1. Well, I will just put US Central 1. Okay, so boot disk change. And for image, so custom images, select my web service. Okay. Click select, click create, select, create. First, click SSH. Okay, to create an environment variable for your load balancer, run the following. Okay. Yeah, so there's something strange. So yeah, it says that if everything works, the command will exit. But yeah, who knows? Maybe it wasn't ready. So now we have this SSH Windows. Now we can export the IPv4 as a variable. Have it noted here. Let's go. Now let's go and verify it with this. So to place a load on the load balancer, run the following command. So AB, what's AB? For benchmarking, you push okay. How many people? Wow. Okay, so this command will stress test our load balancer. Oh fuck. Just like this. Be patient. Okay, so it says check my progress, stress test. In the cloud console. Okay, HTTP monitoring. So complete requests. We can go to sorry, which was network services load balancing. Load balancing, okay. So we go to the monitoring. Something strange is happening. Monitor the front end location between North America. Nothing happens really. Yeah. Oh, okay. So now we have something. So some requests arrived from US zone, US regions. The forwarding role made it implied the selection of US MiG-1. No backend selected. Okay. So compute engine, click on US1 MiG, click monitoring. Okay, so we go to monitor directly the machines. And US MiG-1 should the instance group, not the machines. It's the instance group are here. Okay. Monitoring. Okay, and it says to observe the number of instances and LB capacities. Instances 1, then we arrived at 2. LB capacity, I'm not sure where can I check it. Okay. So here we arrived at 80%. Nice. Depending on the load, you might see the backend scale to accommodate the load. So review, and then your lab. So end lab. Let's close here. So it was good. In this lab you configured. Okay, and your lab. Nice. Now we can continue.
In this lab, you configured an HTTP load balancer with backends in US Central 1 and Europe West 1. Then you stress tested the load balancer with a VM to demonstrate global load balancing and autoscaling. You can stay for a lab walkthrough, but remember that GCP's user interface can change, so your environment might look slightly different. Right, so here we are in the GCP console, and the first pixel...
Yeah, so we skip this. It's just a video about what we've completed now. Okay, great.
Or content delivery network uses.
So now there are some videos which then will lead to another lab. I will just use other 10 minutes to proceed to the next topic until we arrive maybe to network load balancing, not sure. No, maybe it's better to divide it, to keep it in the next video. Maybe these topics are related to each other. So we had this introduction to the application HTTP load balancer, and all looks quite clear. So now we're in 5th position in the leaderboard as we accumulated some more points. And I hope to maybe make another video the next hour so we can sleep, have a nice sleep without thinking that we'll be passed again by someone of these guys. Therefore, thank you very much for being present in this video. And I hope this is useful for you. So let's meet in another video. Bye.